Good morning, good afternoon, good evening to all of you joining us from around the world today. Welcome to this Thermo Fisher Scientific webinar produced in partnership with the AZO network entitled Advanced MicroCT for Non-Destructive 3D Multiscale Analysis. This webinar has been made possible by Thermo Fisher Scientific, so a big thanks to them for enabling us to gather today and share science together. Our first speaker today is Dr. Robert Williams, Assistant Director for Research and Development at the Center of Electron Microscopy and Analysis at The Ohio State University. Our second speaker today is Mark Riccio, Product Marketing Manager for X-ray MicroCT at Thermo Fisher Scientific. Together, our speakers will highlight the versatility of the HeliScan MicroCT, demonstrating the wide breadth of sample types and sizes that the instrument can characterize. Without further ado, I'd like to welcome Robert Williams to the stage. Robert, thank you very much for being here. The floor is yours whenever you're ready.
Thank you, Darius. I appreciate the introduction. Let me echo his sentiments. Good morning, good afternoon, and good evening to all of those attending or streaming this wherever you may be. As Darius said, Mark and I will be giving a talk today about MicroCT. I'm at The Ohio State University Center for Electron Microscopy and Analysis, and I'm the Assistant Director for Research and Development, and then our Director is Dave McComb, and then Mark is the Product Marketing Manager and will be talking as well about the product today. Please check out our websites if you have any questions or want to see some of our facilities at cmas.osu.edu. I just want to briefly introduce CMAS and what we do. It may sound a little odd considering we're talking about the HeliScan, and this is a Center for Electron Microscopy and Analysis. But what we try to do is incorporate a correlative multiscale approach to solving problems. And so what I'm showing here in these two movies you see playing, on the left is a rat spinal cord or a mouse spinal cord that's been serial sectioned by fib-sim. And what I draw your attention to is the scale bar. The edge of the cubes are about 50 microns in length. And the movie playing on the right, you can see the color features in it. Those features are defined by composition. And the scale bar here on this image is 500 nanometers. So we're talking orders of magnitude difference in the size of the features that we're looking at. And what we try to do is, again, scale these and combine imaging signals and spatial resolution with chemical signals so that we understand both where features lie and what they're composed of. So what we try to do at CMAS is bring together sort of a multidisciplinary expertise and combine that with our expertise in electron microscopy with external partners and scientists who have problems that they want to solve, and electron microscopy or X-ray analysis can do that. We're very lucky at CMAS to have a wonderful partnership with Thermo Fisher. You can see here a list of our instruments that we have at Ohio State. All of them are housed in a specially designed facility to reduce perturbations to the microscope, which allow us to achieve better than manufacturer specification on every one of our instruments. We have 6 TEMs that range from being able to see features down to the atomic scale or in between atoms. We have a picometer resolution. We have focused ion beams that are possible to do destructive analysis that are coupled with our SEMs. That's how the mice spinal cord on the first slide was developed. We have a very nice suite of scanning electron microscopes that, again, can probe the gamut of materials pretty much from 1 nanometer up to half a millimeter. And they also work in an environmental condition, which means you can put non-conducting samples in these microscopes. And what we're here to talk about today is the HeliScan X-ray MicroCT. And what I hope I can get across is how this incorporates with this larger suite of instruments that we have and how we can solve world-class problems with it. I draw your attention to the image just above the HeliScan text here. This is a picture of our Titan aberration corrected microscope. And you can see there's two users in the image to the left, and they're behind a glass panel. And this is really indicative of what we've set up here and a way that we've pioneered remote microscopy. And our ability to synergize with collaborators around the world has really, we pioneered this before the pandemic, but over the pandemic, it's become extremely optimized, let's say. Our users sit outside of the rooms of the microscope so that they don't disturb the microscope and the data collection in-house. And in order to do that, we had to figure out a way to utilize the microscopes with almost zero latency. And in that process, we figured out how to do that across the continental United States rather well, and we can even span the Atlantic and the Pacific. And so now, if you want to work with us, you just have to send a sample in, and whenever our operators get on the microscope, the idea is you can log in just as you are now and interface real time, get full resolution of what's going on the microscope, and collaborate. So you can tell us exactly what it is you're trying to achieve. And all of our operators have PhDs, and so they're very well versed in the science and their own research, and so they're here to help you. The other thing that I would point out on this slide is that our facility has been optimized to cancel out or to prevent electromagnetic interference, mechanical vibrations, temperature stability, and power quality. All of these things are very important to getting the highest quality data. And in that regard, we're very confident and very proud to call ourselves one of the best, if not the best, microscope facility in the world. Again, we make that statement based on all of the equipment performing better than manufacturer specification. So what's possible at CMAS? Well, Ohio State is one of the largest universities in the United States. We have 8 faculty, 7 faculty. We're hiring a new faculty as I give this talk. We have 7 faculty who, are world experts in their area of expertise with electron microscopy. We also have a very robust staff. I've put 7 of them on the list here so that you can see if you were going to work with us in CT or in FIB or TEM, these are typically the people you would work with. We also have our cryo lead on here in case there's any interest in life sciences and cryoanalytical work. In 2017, the Nobel Prize was awarded for cryo-electron microscopy. And so in that vein and along those lines, we're really pushing ahead with some of the cutting-edge sciences being performed in the medical field. So just a brief outline of what we hope to get across today, or what I hope to get across today, and what I would like for you listening to hopefully take away. We want to introduce how the MicroCT fits into a multiscale characterization facility, which we have here at CMAS. We're going to go over quite a few examples today that I hope will whet your appetite and really get you excited and show you the potential of what can be done on these systems. And I would hope that as you watch this, what we're showing you, try to extrapolate it to what your material system is or what your problem is. There's going to be multiple different examples that span the breadth of engineering and science. And if you see something that you think you might have an interest in or you want more information on, don't hesitate to contact me at williams.2156@osu.edu. So just a very brief introduction to the HeliScan. Mark is going to talk much more about the technical details and all the capabilities that are provided with this instrument from Thermo. But you can see here, if you look through the various images, we have lithium-ion batteries that we've looked at. We have inorganic-organic composites. So the change in density between the two phases allows us to resolve them. In the upper right-hand corner, we have an African hornet. You can see the shape and the structure of this insect, but we also can see the entire inside of the insect with our data. And so that allows us to now non-destructively look at an insect and make some decisions. Here in the bottom right, we have tissue engineered heart valves. We do research with Children's Hospital, and they do neonatal research on infants that have heart defects. And we are doing research to actually just non-destructively be able to image these valves and pull out spatial resolution and morphology of the valves to understand, one, how they're improving it, but also what some of these defects are. The HeliScan is a rather robust machine. We can vary the voltage of the instrument from 20 to 160 kilovolts. That will determine essentially how thick a component you can look through. We have a 3K by 3K X-ray detection panel, and this allows us to achieve a spatial resolution of up to 400 or down to 400 nanometers, which is, well, this is how we will use this to span our length scales. Our chamber is rather large. We can hold samples up to 240 millimeters in size, and it can hold a heavy load, 15 kilograms. So the thing that really sets the HeliScan apart and is in the name is the HeliScan. It's a helical scanning system, which allows us to traverse large distances and scan in a helical fashion, and that really improves the data you can collect, but also the amount of time it takes to collect that data. So if you act in this field or you do research in this field, this is a simple slide that hopefully can get across what we're talking about when we say we want to do multi-scale characterization or bridge length scales. And the most simplistic way I think I could phrase that is sort of, most people have seen Google Earth now, and you can look at the continent of the United States and zoom in to the point that you can see the streets in a town. In order to do that, Google's accessing the internet and downloading a bunch of data constantly to keep zooming in and provide you with that higher resolution information to go from continent size down to street size. When we work in our microscopes, it'd be great if we could do that, but what we have are instruments that are optimized for each of the different length scales. So the camera that's going to take the picture of the continent is not the same camera that's going to take the picture of the street, just like with Google. And so here we can look at, for metallurgical samples, quite a bit of material properties and structure properties that we would consider important. And we have a variety of techniques at our disposal to probe different size features. And if we have things under 10 microns, we'll typically use the TEM. We can use an SEM as well. The SEM has a pretty large range, and we also can use a FIB. So a FIB and an SEM will be used together in a destructive fashion typically. But if we want to look at larger size features, so for instance, if we're on Google Earth and we're looking at the street, you might want to know what city it's from, and so you zoom out a little bit. We can do the same thing now with a MicroCT. So with a MicroCT, we have the ability to look at a much larger size and volume of the component, so that now we know where the features of interest are that we're interested in, where they're coming from. You could imagine this is a little bit of a poor analogy, but if you were looking at a aircraft landing gear, trying to figure out why the aircraft landing gear failed, you could go in and find the crack and cut that out of the component, but you'd want to make sure you kept track of where in the overall morphology or volume of the actual landing gear the crack was. Was it at the top near the airplane, or was it at the bottom near the wheel, or somewhere in between? And now, speaking on that note, this is just for those of you in the field to give you a little bit of information, but we really we have a new machine that Thermo doesn't develop, and we don't have it either, but that can incorporate into or mesh into this multi-scale imaging, and we call it a MicroCT. And this image here that we have on the bottom left, now the CT can scan an entire aircraft engine or an entire car. You can put this entire system in the chamber, and the system works at 9,000 kilovolts, or 9,000 volts. So our system worked at 160 kilovolts, and this is now up to 9,000. That means we can penetrate through much, much larger materials. So I want to start with an example for those of you that may not be familiar with MicroCT at all, and even for those of you that are. I think most people, when they see this image on the left, they know, they might be able to figure out what it is. It's an Apple Pencil. And so this is an article that was recently published by CNET looking at the Apple Pencil, and they wanted to do a teardown and see what the components were and how it was constructed. So as you can see, there's a person cutting the pencil in half with a Dremel tool. And when you do that, you have, on the right, you have multiple layers that wrap and encase the pencil. Note that they have on protective gloves because these sharp edges are probably razor thin. And then you can actually extract a computer chip. So you can start to see the components and the electronics that actually help control and run the Apple Pencil. So when you look at this is something that traditionally, you could use for quality control if you wanted to know how well the component was built. You could use it for a forensic analysis, trying to understand why the component failed or what were the components in the system. You might imagine that you've bought something and you don't know if it's truly an Apple Pencil. So you're questioning whether it's OEM versus vendor components. So again, tearing this down and seeing what's in there, looking at this chip, you might, if you know what to expect, you could do that. Something else that you hope isn't going on with Apple Pencils, but this idea of cybersecurity and chip architecture now, the ability to probe these chips and actually look at the architecture with which they're built is sitting at the forefront of cybersecurity. So, we really are at the point where we need to make sure that the chips and the semiconductors that we're putting in our systems and in our phones and in our pencils aren't transmitting signals elsewhere or essentially spying on us. And so again, this becomes very important from a multiscale aspect, because you'd like to look at the chip at something of this resolution and then be able to go in closer and look at actual architecture of the chip. So after this teardown, this is what we were left with. We have a pencil that's broken in half. You have a bunch of metal components all ripped apart, and it's never going back together. And if you're working in another area, you may want your component to stay together and be able to interrogate it. So is this really the optimal technique? Technology's improved significantly, and so we'd hope that we can, give you a better method to probe your material or your engineered part. And this is where MicroCT can really play a role. And so on the left, I have an Apple Pencil, and you can see our source for our X-ray MicroCT. This is what it would look like in the chamber. I would point out how simple it looks to load. You just have to get the sample in the microscope or get the pencil loaded in the microscope. And now on the right, we have a 2D visual or virtual slice. And so after collecting the data, you can pick any plane in the material you want. And one thing that's really amazing here is that the pencil is 166 millimeters tall. And with one scan, we can scan the entire pencil from top to bottom. And so now you should be able to see a movie as we scan down the component. You'll see a lot of interesting little features popping up. Some people may think this is Elon Musk's spaceship, and these are living quarters to go to Mars. As we get down to the bottom of the pencil, you're going to see some vertical features that are very periodic right here. And so these features are actually the battery that's used to power the Apple Pencil. So now you can actually think about, if you're interested in battery technology, this could be a very nice opportunity or technique that would non-destructively evaluate your batteries, and you could use it to identify defects or features of interest. So I just alluded to this, but with one scan, if we think back to the picture that was destructive from the CNET article, that you saw all the components laying on the table, now we can see all the various layers of this pen in these 5 different images. In the top 3, we're looking at different levels of the outer casing and the middle casing and the inner casing. And the 4th image down, you can start to see chip structure. And these very bright features on the bottom of the pen, those are the neodymium magnets that are used to keep the pen stuck to your iPad. And then if you're interested in the chip and the architecture, we can get rid of all of the outer casing now and actually look at the electronic chips that control this, this component. And again, what's really amazing with this is with one HeliScan full field visualization, you can collect this data with 9 micron voxel size. So that means you're probably going to see anything under somewhere around 20 microns of image resolution. And this is ideal because if you don't know what you're looking for, and even if you do, most people want to have a frame of reference to show the people that they're presenting their data. You may know where you got the sample from, but how do you present this data? Now we can use something like this as a map or a roadmap to where the components came from. Now this is the same data set. We've just increased the magnification to where we're looking at the front portion or the tip of the pen. And you can see the same thing. We can change the layering. We can look at a subset of it. And again, this is 9 micron voxel. So you can see the very tip of the pin in the bottom right image. And you can see the component that's used to test the flex and the force. You could measure the thread count to see if they're using the same metallic component or thread for the screw. And again, I can't speak highly enough about how important this is for feature identification and sort of a frame of reference. So now if I take one of these 2D slices, you can see this in the top of this slide. We have a black and white image. This is just, it would be what you would expect if you cut out a thin piece of material right through the cross-section of the pencil. And I want to draw your attention to what I alluded to earlier, which is the vertical, or in this case, the horizontal features that are encased in the green box. This is where the battery component of the pin is held. And so what we can do, just like we were looking at the tip, if we focus in this area and look at the data more carefully, you can zoom in now and you can see these horizontal periodic structures that I was talking about. These are the cathodes and the anode regions of the battery. So now you can actually start to interrogate what battery is present. Is it the proper type of battery in this pin, all before you ever take the pin apart? And as you look at this, you might say, well, I'm interested in things of a better detail or finer detail. And so this scan was collected, again, as a full scan with 9 micron voxel size. We have the ability to go in and collect a higher resolution region of interest scan in areas once we locate them. So that's what this large area scan is so powerful for, is that you can locate regions very specifically that you would like to go pull higher resolution data from. And this slide here is a region of interest data set, we would call it. And now we have a 1 micron voxel size. So we've almost increased our resolution by an order of magnitude. And if you can see my yellow arrow, it's pointed to a little spot. And maybe you can't see that, but if we increase it a little bit, here you can actually see a circular bright feature. And in X-ray CT, the bright feature is going to relate to a more dense material. And what's really amazing is that when we go to this region of interest scan with 1 micron voxel size, we can actually image higher density impurities and inclusion on the left. And on the right, we actually see voids and lower density regions that we would most likely associate with delamination in the cathodic layer. But we don't know, let's say. We'd like to look at that a little bit more in depth. And so everything we've done up to this point has been non-destructive. And this is where I take you back to where I started with the instruments in our facility. What if you wanted to go in and maybe perform a destructive analysis? Let's say we went in and wanted to cut this region out. We've now identified regions that have defects, and we can go in and very locally and site-specifically remove these portions of the material, put them into the TEM or the SEM, and we can start doing chemical analyses and even higher resolution analyses on these materials. And this is really a game changer. And this we think has a huge opportunity going forward, so that we have the ability to, on a multi-scale, characterize materials and help answer problems. So I want to switch gears here, but stay in the same vein of this correlative multiscale. We were just talking about an Apple Pencil and how we could extract a site-specific location out. Teeth sensitivity is something that is rampant and running, or very common in humans. And without going too much into that side of it, we have companies that make Sensodyne toothpaste and teeth sensitivity toothpaste. And so we work with GSK, and they have a product that is supposed to occlude the dentin tubules. It's supposed to help reduce teeth sensitivity. And in order to do that, you need to block the tubules. And so what we would like to know, and what we'd like to be able to do, is look at a tooth, apply Sensodyne toothpaste to it in a very rigorous fashion, and then be able to systematically go through and say, yes, this is actually occluding the particles of the tooth, which will reduce teeth sensitivity, or no, GSK is just making this up and they're using it as a sales pitch. And what's really great about GSK is that this isn't something we're going to do proactively. GSK wants to make sure that this is true, right? GSK very much supports their scientific backing and patents. So this is something that works very well for life sciences and consumer goods and toothpaste. But I hope you can imagine maybe in a 3D printed component or your material system where this might apply. And what we're going to do this is use X-ray microtomography. On the right hand of our slide, we're going to use X-ray microtomography to see sort of a more macro scale. We're going to identify individual dentin tubules. These tubules are going to be around a micron in diameter. And then we're going to go in and remove those tubules so that we can put them into the TEM and actually do chemical analyses and see that the Sensodyne toothpaste is actively working. And so these are going to be a few movies that show what we were doing. And so to improve our resolution, what you're going to see in this movie is that we cut a periodic pattern into our dentin. And now we're zooming out and showing the tooth. And it's going to show you where the slice came from, what slice we have. Very easily, with density differences, you can identify the interface between the enamel and the dentin. And again, this is a full field scan. This isn't the highest resolution. But after identifying that region, you can see we're using a tooth that's about 8.5 millimeters in diameter. We pattern in these pillars, and each pillar has an edge that's 250 microns by 250 microns. And so what you're seeing is X-ray CT data where we can go in, we can visualize. And after doing this now, we can actually see where the dentin tubules are. Now, these tubules run directly towards the nerve of your tooth. And so what we need to do is see that Sensodyne toothpaste, when exposed to them, is occluding those particles. But let's say you're working in some material that has a very tubular structure. You can imagine that flow is important, and understanding tubule interconnectivity and flow rates is important. So you could take something like this, scan, and get a nice internal picture of your pore distribution and your tubule distribution. And again, similar to what we just did here, we've modeled it. So now, once we know that there's dentin tubules and we want to go in and see how the Sensodyne toothpaste is working, we can go in and keep track of where we are in the sample and actually go in and remove a portion of the sample. And so what you're seeing now as this movie zooms in, this is an actual TEM image of an individual dentin tubule. The dark contrast that's on the outside of the image, those are actually individual collagen fibrils that you're able to image in the TEM. And now you see this very bright circular region or bright casing on the interior of your pore. And that is indication that we have Sensodyne actively working here. Now we doped the Sensodyne with strontium in order to control our experiment and be able to identify this more clearly. But the concept here is you can take a HeliScan image in order to find features or defects of interest and then go in and remove them out very precisely so that you can characterize them with other methods. And now, again, if you go talk to your boss or you're going to show this to an auditor, they often could care less about what I just said, and they want to know, well, did you actually get it out of a tooth? How do we know that happened? And so, again, we can come back here and look at this and see where we came from. We have a good idea of exactly where the material was extracted, and all of this was done essentially non-destructively until we got to the point of extracting the dentin tubule. Another life science application, well, you can use this for many life science applications, I should say. One thing I'd point out on this slide is that these are photographs of actual samples going into the microscope or into the CT. Note that the sample preparation doesn't look too crazy. We have a little sample in a cylinder here on the left. In the middle here, we have a little bug. And over here to the right, we actually have a worm that's hydrated in fluid. Right? So it doesn't, if you're using electron microscopy, you can't really have a bucket of water in your microscope. We're at extremely high vacuums. This is run in a vacuumless system, and so you can encase the material in anything that is low attenuating to X-rays. And so we've used MicroCT data to collect quite a bit of info on animals. So we've looked at bone and heart and brain. You can look at skin. Plants and insects work very well, so we do quite a bit of work with entomology engineers or scientists. And so if you're in the life science application, realize that there's quite a bit that can be done here. And due to the low density and the nature of the material, it works very well. And so I want to talk a little bit about some work we do with a scientist named Hong Mei. She likes to look at honeybees. And this is not exactly a honeybee, but if you're working on insects, just as I alluded to the African hornet, one scan of this shows you the entire structure of the hornet or the bee. And so you may have a defect you're looking for in a bee. Maybe not every bee has whatever it is you're looking for in it. And now you could use this scanning method to actually identify the exact bee that you're looking for. Maybe there's a deformity in the torso, right? So remember, it allows us to non-destructively see into our material, whatever it is we're looking at. And so Hong Mei is very interested in honeybees. And what she has done and what people have done traditionally over the years is they use tweezers and scalpels to do dissections. And, if you've ever looked at a honeybee, the head is very small. So this is very delicate work. Now with CT, you can image this entire structure very accurately. You can see here on the left in our black and white images, 2D virtual slices, and we can look at cross sections of the bee mandible. We can understand how the porosity and how the structure is formed. You can go through and look at how it relates to the cranial of the bee head. You can also see the very fine hair-like structures that are on the bee mandible. Now, what Hong Mei wants to do and what she has been implementing here is, if you can get these three-dimensional reconstructions, you can also produce CAD models from them, which means now she can go back and 3D print these models for other students to learn from, or you can now blow it up. So a bee head that's usually, at 5 millimeters in diameter, you can print out a bee head that's now 5 inches in diameter, and use this from an educational and a training standpoint, but also for yourself to better understand where this goes. And when you think about CAD models, I want to use that as a segue here, is because you can use the CT to produce CAD models of your features so that you can recreate them. But you can also quantify this data. And so quantifying this data is critical. I would hope most of you that I'm talking to here, as engineers, we want quantitative outputs. And that's what CMAS is really good for. We like to do our best to provide quantitative data sets so that whether they're being used for modeling inputs or machine learning inputs or just statistical analyses, they're accurate and they're quantitative so that you can now run rigorous routines to better understand and perform predictions. And in that vein, additive manufacturing and 3D printing is one of the hottest fields now. A lot of people now are just going out to different centers or different stores and buying 3D printers and putting them in their house. And when you do that, you need to understand the material that you're putting into it. The assumption is often that you're using, or if you were to take a piece of metal and put it in a 3D printer and print it out, a lot of people would think, well, I have the same properties that I have if I have a conventionally forged or fabricated material. And that's not the case. And so we have a lot of researchers here at OSU and across the country working on understanding the powder that goes into these systems and how that affects the resultant product, but then also the resultant product and how to improve that based on the processing and the parameters that you use. So first in that light, this is a simple image here showing gas atomized titanium powders. So this is a Ti-64 powder system. And what you can see with the rotation of the movie is a very nice color image. We've discretized each of the particles so that they can be quantified. That's what the images to the top left are showing, is how we go through and do some segmentation and object identification. But what's really neat is you can identify the pore size and come up with statistical quantification of the pore size, of the particle size, but you also can image the pore size. So inside these little particles, there may be voids, there may be holes. And so this technique is robust enough to be able to see the holes in the particles, but also see the particle surfaces themselves. And so this can be applied to a number of fields, and just some of them would be in 3D printing for aerospace and automotive. You can imagine for pharmaceuticals, looking at the contents of your pill or the shape of your pill and things of that nature, and consumer goods. And then I hope that some of you listening will have applications that I'm not aware of yet, and we can discuss these. Now, I alluded to this is, again, we want to perform quantitative analysis, and so that's what we want to pull out. And again, you can see this pretty image. You can see what your average pore size is. The question becomes, can we get quantitative enough that this can be used for statistical analyses? And the answer is yes. We certainly can. So it's a real opportunity here for modeling and machine learning to develop statistically representative volume elements. And that's something that we want to work towards, and we're happy to collaborate on. Now, following in this powder example, we have a very nice additive manufacturing facility here at OSU. And so if you take these powders, they can be used to 3D print scaffolds for human use. So, or at least that's the attempt, right? We want to mimic scaffolding that would be used in the body currently by conventional methods. We'd like to use 3D printing to print, specific scaffolds. So imagine you could measure someone's aortic cavity and print out scaffolds that fit perfectly into their aortic cavity, as opposed to how it currently works. And what we have the ability to do after 3D printing this is we can have a voxel size of around 315 nanometers because the sample is so small. And in the top image, you can actually see where the pore structure is. But in the bottom image, we've actually with very high fidelity recreated the surface. So now you can look at surface topography and surface roughness and see what's going on. That's important for the scaffolding, but it's even more important if you take a CAD model. And so a lot of what's going on now is trying to print out very complicated components that could never be formed by another method. They couldn't be forged, they couldn't be cast, and they can't be machined. Well, here on the left, we have a CAD model of a gas injection nozzle. And the CAD model is perfect. And so what you would hope is when you do your 3D printing, you have a similar perfect structure. And what a 2D virtual slice of this 3D printed component shows us is that's not the case. So now we can look at internal porosity. We can look at how the material overhangs, and do we have really a near net shape? You can look for density inclusions, and you can very well look at surface roughness. This can be a game changer, for validating your additive manufacturing and your component geometry. You can use it for quality assurance and quality control. And where we really like, from an academic standpoint and an integrated computational material science aspect, let's bring in all these quantitative inputs and see how can we mix those in and combine that data, one, to improve the 3D printing process, two, to understand the microstructure property relationships, and three, to end up how do we get the proper powders to give us the features we want. And so it's a very big effort, but that's what we have here is a big team, and hopefully we could discuss ways to do that. So I want to move it along to Mark here, who is going to talk more about the technical side of how this is done. But I would hope, just as a quick little summary of what we've talked about here, I would hope I've gotten across that, these data sets from the CT are extremely information rich. They are chock full of information, and we need to just collect the data and then go in and pull it out. But the versatility of the machine allows us to look at really almost any type of material, as long as it's not too dense. And so in doing that, we can get an imaging and visualization of the features non-destructively. We can do feature identification to figure out where further analysis should be performed. And then what we really like to do is this multiscale correlative characterization, right? Where we can combine CT with analytical electron microscopy to give you structural information as well as chemical and phase information. So thank you very much for joining us today and your time. And I want to pass this along to Mark.
Thank you so much, Robert, for your presentation. We're going to keep the ball rolling, like he said, and I'd like to welcome Mark to the stage. Hello, Mark.
Hello, Darius. Good morning, everybody. Good afternoon. Good evening. I would like to continue talking about non-invasive 3D X-ray MicroCT And I'd like to focus a little bit on some of the technology highlights that the HeliScan can bring to all the examples that Robert gave from CMOS, which is definitely a world-class facility for imaging. And I really appreciated his super impressive results that he just went through, and I'll go through a couple more, as well as talking about some of the extended solutions that you can do with a HeliScan MicroCT with 4D and in situ experiments, and then we will conclude for today. So in terms of the HeliScan, some of the special, unique features about this MicroCT from Thermo are that, as you saw from Robert's example of the Apple Pencil, it can acquire very large volumes with one scan, and we'll talk about that more through the rest of this little discussion here. It can acquire using both tungsten filament, which is what most MicroCTs use to generate X-rays, as well as a Lab6 filament. And that enables you to get down to 400 nanometer resolution. And it also gives you a different X-ray spectrum, which has different sensitivity, which for certain samples is going to give you a higher, better ability to discriminate different densities in your samples. You can also zoom in, and Robert talked about the ROI scan and zoomed into the battery on the Apple Pencil there. You can zoom in on your sample to achieve a higher resolution than you would when you're capturing the full field or the full sample, typically 4 times, sometimes a little bit more. And you can also acquire off-axis types of scans. They don't have to be right in the center. We have a stage that allows the sample to move and accommodate. We can bring in large samples. We can bring in bigger than 200 millimeters. We can scan 200 millimeters, and we can go all the way up to 160 kV for energy. We've got different trajectories in terms of acquiring your samples. Most MicroCTs typically use a circular projection to acquire their data. We can do circular. The HeliScan can also do helical scans, and double helix and space-filling helical to go faster. So the reconstructions are both iterative, and we can pull out phase reconstructions. And the HeliScan also plays very nicely in Thermo Fisher multiscale, multimodal workflow. And this is partially what Robert was presenting earlier, where you can use the HeliScan to begin your journey down to the atomic scale. So fantastic. So with this movie, you can start to see inside the lead box. It's leaded so that you don't have to wear a dosimeter and you don't have to worry about radiation inside the room with your HeliScan. On the right is the X-ray generating source, and the center is the stage, and the left is a very large X-ray detector. Great. Now, some of the magic that lives inside the HeliScan is displayed here during an acquisition of a sample. Normally with MicroCT, the sample rotates to acquire your projections. And in this case, it rotates and moves up and down at the same time. And that gives you the helical trajectory. And that allows the very large volumes to be acquired without having to stitch multiple scans together. As Robert scratched the surface of potential applications, I also will only scratch the surface of potential applications for this instrument, ranging from glasses and ceramics and metals and polymers, so low density stuff, high density stuff, of course, batteries and additive, semiconductors, life science, and everything in between. So as I present these examples, if you don't see the favorite sample that you work with, try to imagine, since X-rays don't discriminate, they love anything that has density changes, that your sample also would be very interesting to look at. I want to mention that after you've acquired the data with a MicroCT or the HeliScan, you need to be able to leverage the value that's in that data set. And we use Aviso software. This is a Thermo Fisher owned software, and it is fantastic at being able to do the 3 things that I would want to do with the MicroCT data, which is start with visualizing the data and understanding what's in there, then analyzing that data so that you can begin to understand your sample. And sometimes visualization is enough, and sometimes you have to take the next steps and go to the analysis. and other times you really have to iterate amongst all those several times before you become really able to describe and truly understand your materials. In terms of the quantification, this is just a few of the quick things that a VISO can do. And just to give you an idea, everything from the simplistic measurements to advanced measurements and modeling capabilities really can bring you through basically a plug and play environment. You can certainly write your own code. The VISO spits out a nice TIFF stack, so you can go into any program that you like. But the VISO will allow you more of a situation where you don't have to write the underlying code to be able to do sophisticated 3D visualization and sophisticated and advanced analysis. Okay, great. So let's start with a simple generic sample where pretend we had just done a HeliScan, helical scan, and we have a nice 3D data, and we're visualizing that data, and we're looking at it. Okay, it looks nice, great. Maybe we're going to do a little bit more sophisticated analysis and thresholding and changing of what we look at. Now we can see pores and we can see substrates. Okay, great. And now we can see more pores. And now we look at dense particles. And the thing to note here is that on the right, as you look at those dense particles, they are certainly not what I would call equally distributed amongst that volume. They're very heterogeneous spatially along the sample. So if you wanted to take an approach where you're using the HeliScan to be able to use higher resolution data to examine the structures inside, you would take that scale of data that you've acquired and you would look for a region where you want to zoom in and do a region of interest scan. And here we've shown you pick an ROI, a region of interest at that particular spot. So then we can do a subsequent zoom in scan and get higher and higher resolution to be able to look at the smaller scale structures. Okay, great. Looks good. If you did the same approach with a traditional circular MicroCT scanner, this is what you could end up with, where you've done your scan on the left at the macro scale, and you try to pick a region that you think is sufficient and reasonable and adequate to represent your sample, and you pick an ROI, and you zoom in, and you do another scan, and then you get all the way to the right-hand side, and you're analyzing that, and you ask, did I get the correct result? So one of the things you have to wonder and ask is, what's the probability that you've acquired a representative area when you do your zoom in scans to do your analysis and understanding? And of course, that's different depending on different samples. But as you can see in this particular example, there would be a strong penalty for not being able to understand or initially see where the region of interest might really be, so that you can understand the true structures in your sample. And sometimes you even might have to take multiple high resolution scans to be able to adequately represent and understand your sample. Very good. Here's a typical battery example, and this came from our colleagues at University of California, San Diego, Shirley Mangel's lab. It's a battery example, but it's also generic, and that is that people that bring samples in to be analyzed and examined with a MicroCT often ask, what can I see inside? What can I do with the data? Am I going to be able to trust the data? Am I going to be able to get statistics that are valid for nature? Am I going to have a high enough resolution? How do we quantify, or can we quantify with our advanced techniques that we already know how to do? And can we leverage the HeliScan data into our multimodal workflows? So this particular work that over the next couple of slides is online already at Archive there, and it's been submitted to a nice high impact journal. So keep your eye out for this paper in the future. But what we're looking at here is a cathode, different layers here with different conditions that made these, and they want to be able to examine each different layer, each different condition, all at the same time, of course. So if you bring this sample in, we would do a helical scan. We would capture the entire sample so that we make sure we get all the layers, don't have to have artifacts that may be introduced by stitching together multiple volumes. And that's great. And that may be enough to do all the things that they might be able to want to do with their sample, might be all the things you want to be able to do with your sample. By the way, this is a virtual slice on the right-hand side after we've done the tomography, where we have many thousands of slices, and we're taking one slice in that virtual data set. And on the left, that's an image that you might see if you had brought the sample to the dentist's office, where they do an integrated X-ray, where they have the X-ray on one side and the detector on the other. And what you're seeing there is an amalgamation of the entire sample, not a single virtual slice through it like you see on the right-hand side. So that's pretty high resolution, might be good. But if you needed higher resolution, then we would leverage the Lab6 filament and be able to pick a region of interest and zoom in even further. So now we get the voxels down to 190 nanometers. And now we can really see the information about the particles and about the binder in between, and be able to do some further, more advanced analysis on that sample. Okay, great. So that can be summarized in this kind of a cartoon, where on the left we have one scan from the HeliScan, and in this case 190 nanometer voxels, and the HeliScan has a very large detector, and you get a nice large volume. And had you done this on a traditional MicroCT, where you might be running in bin 2 mode, so your effective detector is a K by a K, you'd have to stitch together more than 50 scans to capture that same one volume that you got with the HeliScan. And then, of course, you're going to have all kinds of computational issues and artifacts that go along with doing that. So there's a strong advantage to be able to capture a very large area with one scan. I'm only going to scratch here for a second as a reminder that Robert mentioned in his talk a wonderful instrument that can go up to 9,000 kV, and that's fantastic with 2 meter by 2 meter samples, and that's excellent. But of course, that lacks the highest resolution. So with 160 kV, there are still 1,000,001 samples and examples that you want to be able to take advantage of this kind of technology. So with 160 kV, you can definitely go through metal. This is titanium. So I just wanted to show that it's very possible, looking at a 3D visualization, looking at some 2D slices, looking at an area where you can zoom in even further to be able to find those internal characteristics non-destructively at high resolution. Great. Another thing that the HeliScan can do is leverage that Lab6 filament to get very highly sensitive data sets from which you can extract phase contrast information. So you can see on the left in a standard reconstruction, and you can see on the right if we utilize our phase contrast retrieval in our reconstructor. And of course, that can make all the difference in terms of the analysis of your sample, where on the left, maybe it would take you a year to by hand with your brain go through and identify each of those fibers. And on the right, now we're talking about a problem that a VISO can tackle in 1 to 2 minutes and be able to analyze that entire sample. So when you look at being able to leverage your analysis, data is paramount, of course. And if density is insufficient, then you want to be able to have the opportunity to utilize and bring out the phase information. And so the HeliScan allows you to do that, and you can see the wonderful results that you can get. One of the other very fun things to take advantage with the HeliScan is, since this is 3D, non-invasive, non-destructive, you can do a 3D scan and then change the condition on your sample and do another 3D scan and change the condition and so on and so forth, and end up with 4-dimensional data sets. And you might want to do that perturbation in the HeliScan on the stage. So Deben sells some very nice plug-and-play rigs where you can put your sample and change the tension, change the temperature, and do those experiments inside the HeliScan. And I'll have a baffle option on the HeliScan so that you can route your cables and cords to go outside. It's not, it doesn't preclude cabling, so you can set up your experiments outside the HeliScan, and that's advantageous for doing those types of experiments. And at the end of that, what you might end up with is a 4-dimensional data set that you can not only visualize, but also analyze. And perhaps you want to go, as our colleagues at Australian National University did, to finite element model and do your analysis. So this is virtually slicing into the sample. And you can start to see it move here. That movement, each step in the movement is a 3-dimensional scan. And you can see the crack in that particle forming as the tension was changed, as it was compressed. So you can begin to ask and answer the questions, where are the failures in my structures originating? And of course, the 3D non-invasive power of this technology is what allows those types of experiments to happen. So that's a fantastic state-of-the-art utilization of your 3D MicroCT. As I mentioned before, the HeliScan plays in a very nice environment of multiple instruments ranging from SEM all the way down to TEM, and you can do this with both software and hardware. And the hardware here that I want to reference is a common holder. So you can have your sample on a holder inside the HeliScan and bring that same holder to our SEM. And if you want to put that in, here's an example on the right-hand side where we have PFib data married with the MicroCT HeliScan data sets. And now you're bridging the multiscales and multiphysics capabilities of other modalities into one data set. And we do that using our MAPS software that can bring in any data set that you'd like and put them all together. And when you're doing MicroCT and you want to find structures that live inside and underneath the surface, then you identify them with the HeliScan, and then of course be able to probe that at nanometer scale with the other instruments. And so MAPS allows us to work in that environment very well. So to conclude, today we went through some really unique advanced hardware and software, and of course the CMOS collaboratory environment for solutions. And the HeliScan allows us to play in many different domains, from the material science engineering domains to, of course, geology and electronics and life science, and then span into industry and do QA, QC or failure analysis and process optimization, all powered by the helical scanning and the high resolution from the Lab6 down to 400 nanometers and phase contrast when necessary, and also being able to leverage our Thermo Fisher Scientific workflow to get the true multi-scale information. So with that, I want to say a lot of thank yous here to Darius and colleagues at AZO, to Dave and Robert, Carly, Dan and colleagues at CMOS, and to David, Dirk, Franta, Rafaela, and others at Thermo. Without everybody's support here, this webinar wouldn't have happened. So thanks to all of you for working behind the scenes so hard, and your enthusiasm and support for all this. And so for everyone watching today, thanks very much for coming. And we do hope to hear from you so we can share this world of science, discovery, and honestly, the thrill of X-ray imaging and beyond. Thank you.
Great. Hello, everyone. I hope you enjoyed those presentations given by our esteemed speakers. I'd now like to invite them back here on the stage so that we can have a question and answer session. We have time for just a few questions here. And as a reminder, if you have a question and you'd like to ask the presenters, you can submit it using the Ask a Question panel beside the media player. So we'll jump right in here. The first question I have for both of you is, have you ever looked at pharma samples with API?
I can say yes to that. I would assume by API, I mean you mean active pharmaceutical ingredient. We actually have used that in the correlative workflow. We use the CT to determine the size of the particle, and then we have used FibSim and cryofibsim and cryomicrotomy to actually section into the particles and produce higher resolution scans of the pill or particle that we're looking at. Mark, do you have any images of that? Or
let me see. I have 1,001 images. So let me see if I can pull one out here. Let's see. How about? Okay.
That would work.
Here, sorry.
That would work. No, that would work. That looks perfect.
Okay, yeah. This is a Pharma tablet, obviously. Scanned on the left is the original tablet. On the right is the scanned 3D information. Looks like a virtual slice in half here on the right-hand side at 4 microns. And this one, okay, this is a region of interest zoom in. So we wanted to just zoom in and see what kind of resolution and what kind of structures we could pull out. And so now you almost, as Robert said, you can start to pull out the particles, and we want to zoom in, I think, a little bit further to see what's possible. Okay, right. So when we want the highest resolution, maximal sensitivity, we would switch over to the Lab6, and now we can see the multiple, not only the dense particles, but the multiple phases of some of those low density materials inside this pill to be able to pull out API as well as segment out if you're asking questions about how much of it is there, volumes, and this plays into the 4-dimensional aspect as well, because if you want to watch what happens to this material over time under different perturbation or different situations or different environmental conditions, then you would watch what happens to these scans over time in terms of not only their high density particles, but also the lower density API information at high resolution before you go down to the destructive modes that Robert was talking about in the nanometer scale.
Great. We are over time, but I'm going to push us to just one last audience question here. Would the spatial resolution be different when using a circular or helical scan while other parameters are kept equal?
I'll leave that to you, Mark.
Yeah, I hate to say this. Oftentimes, if people ask things about MicroCT, the answer that often comes out is, quote unquote, it depends. So I would like to be able to say no, but if I said no, there's going to be an example where it's yes, there is a difference. So I'm going to leave it to an it depends. And I'm sorry I have to answer like that, but on occasion it's true.
Okay,
great. We'd be happy to entertain any kind of follow-up if you have a particular sample and you want to find out in your particular sample if there's a difference. We're happy to do demonstrations and go through exactly that kind of experiment. Thanks.
Great. Thank you very much, Mark. I think I will bring it to a close there. Thank you, everyone, for attending this webinar. In closing, thank you again for taking part in this Thermo Fisher Scientific webinar supported by the AZO Network, and we look forward to sharing science with you again in the future. Have a great day, everyone.